In this video, I'm going to go through as thoroughly as possible examples of molecules and their geometry. We're going to construct their Lewis dot structures, and we will see from the Lewis dot structures how we will be able to predict what the geometry of the molecule will be. We'll know what the shape is, and we'll know what the angle is between the bonds that make up the molecule. So let's begin with this compound, beryllium dichloride. So the first thing I want to do is compose its dot structure. So we know that we start off by getting the total number of valence electrons, 2 from beryllium because it's in group 2, and 7 from each of the chlorines, for a grand total of 16 valence electrons. We then arrange the atoms, joining them with single bonds, putting the least electronegative element in the center. We join them with single bonds to begin with. I've used up 4 electrons, 2 pairs. I have 12 electrons left. I then go to the outer chlorine atoms, and I want to distribute these until each chlorine has an octet. And when I do that, I can see I've used up all of my valence electrons. There are none left. I examine the beryllium, and I see that it has only 4 valence electrons, but I know, in fact, that that is okay because beryllium is one of the exceptions to the octet rule. So there's my dot structure. Now, I want to utilize the VSEPR model. Remember, that's the valence shell electron pair repulsion. I'm going to look at the atom in the center, which is beryllium, and I see that it has 2 bonding pairs joined to it. I know that electrons have a negative charge. These electrons actually are orbiting back and forth between the beryllium and the chlorines. And these electrons are in what we have come to know as clouds. Electrons are negative, and so if I bring electrons near each other, like charges repel. They're going to want to be as far away from each other as possible, and with only 2 pair, that would be arranging them so that they are pointing in opposite directions from each other, which forces these 3 atoms to be arranged in a single line. So this is going to be a linear molecule. And I know that arranging it this way, the angle between those electron pairs will be 180 degrees. And this is, of course, a linear molecule. So the electrons are trying to get as far away from each other as possible. They can't just simply go off into space and totally be isolated from each other. They're going to get as far away as they can to reduce to the greatest degree the repulsion. There'll still be repulsion, but this is at its lowest level. That's a linear molecule when you have 2 pairs of electrons around the central atom. Let's go to a second example, which is boron trifluoride. Again, we need the dot structure for this. We add up the valence electrons, 3 from the boron, 7 from each of the fluorines for 24. We put the boron in the center because it's got the lower electronegativity. We join them with single bonds. I've got 18 valence electrons left. I go to each of the fluorines and give them 6 apiece, so they end up with their octet. I have none left. I go to the boron in the center, and I see it has 6 electrons from those 3 pairs. We do not have an octet, but again, boron is one of the exceptions that is allowed, and so this is the correct Lewis dot structure. Those 3 pairs then, I go to the central atom, the boron, and those 3 pairs around the boron are repelling each other. They're in these clouds, electron clouds that they're orbiting in. There's a repulsion because they have negative charges, and they're going to get as far away from each other as they can. And in this situation, when you get 3 pairs, they will point towards the vertices of an equilateral triangle. By arranging them in this way, there's 120 degrees of separation between those electron clouds, And I then describe the shape that is produced as a result of this arrangement. And of course, it looks like a triangle, and they're all in the same plane. So this is called trigonal planar. So when you have three pairs of electrons arranged around an atom, the farthest away you can get them is 120 degrees, pointing towards the vertices of an equilateral triangle. Let's go to a third example, and this one is methane, CH4, which is one of the components of natural gas. I need the dot structure if I'm going to figure out its geometry, and I've got 4 electrons from the carbon, because it's in group 4, and 1 from each of the 4 hydrogens for a total of 8. I put the carbon in the center. I arrange the hydrogens using single bonds around it. I've used up all 8 valence electrons that were available. There are none left. I check the hydrogens. Now hydrogen only needs the first shell filled up, which is a pair of electrons, a duet, and they all have their duet. And then carbon has 2, 4, 6, 8 from those 4 pairs, bonding pairs. Everything is satisfied. They're all electronically stable, and that's my dot structure. Now to get the geometry, again, I want to look at those pairs that are around the central atom. There are 4 of them. Now, your inclination might be to say, well, this is already the shape. They're going to form a kind of square, and that would give a 90-degree angle of separation. And that would be true if we were restricted to a plane, but we're not restricted to a plane. We can arrange these in 3 dimensions. And so we get a figure you probably aren't acquainted with, and that figure looks something like this. And by arranging the hydrogens this way, now they're not in the plane. I've tried to make this look a little bit 3-dimensional. The 3 lower hydrogens are kind of pointing downward away from the carbon, sort of like the legs of a tripod, and then the 4th hydrogen is pointing straight up. And by arranging this way, I get an angle of 109.5 degrees, which is bigger than the 90 degrees you would have had if you were restricted to a plane. Well, this is a special structure I'm sure you've never run into before, and the name of this is a tetrahedron, which means 4-faced. So every 3 non-collinear atoms defines a plane, and so we could count up 4 faces on this structure. And if you look at the pictures, the diagrams in your book, you'll be able to see that it's 4-faced, and this is a tetrahedron. So when you have 4 pairs of electrons around the central atom, you can get them 109.5 degrees apart. Let's go to a 4th example, and this is phosphorus pentachloride. We want to get its geometrical shape, and we start off by, again, adding up the valence electrons to get the dot structure. I have a total of 40 valence electrons. I put the phosphorus in the center. I arrange the chlorines around it. I've used up 2 electrons for each pair. I've used up 10. I have 30 left over. I start on the periphery and I take care of all those chlorines. They each need 6 apiece, and that would mean all 30 valence electrons that were left are used up. There are now none left, so all the chlorines have their octets, and I count around the phosphorus and I see that I've got 2, 4, 6, 8, 10. I exceeded an octet, but that's okay because phosphorus is in row 3 or below, where we have more room to accommodate the extra valence electrons. Okay, with 5 pairs then around the central atom, again, probably getting a figure you've never run into before, you're going to get something that looks like this. And when you look at this carefully, again, I tried to give the flavor of this being 3-dimensional. The phosphorus and 3 of those chlorines are kind of going across the middle of the structure, and then it looks like I've got a chlorine above and below the phosphorus. So those ones that are lined up through the center form an axis, and those are axial, and there's 180 degrees of separation between those pairs of electrons. Those ones cutting across the center, those are in the equatorial position, and they point towards the vertices of an equilateral triangle, which means I get a bond angle of 120 degrees. And then the third angle is the angle between the axis and the equator, which is 90 degrees. So there are three different bond angles in this kind of arrangement, and this one is known as a trigonal bipyramid. Bipyramidal is an adjective. And so what it literally means is I've got two triangular pyramids. Pyramids are named by the shape of the base. So if I look at the top half of the molecule, I've got the 3 chlorine forming the base across the center, with the top chlorine being at the vertex of a triangular pyramid. And if I look at the bottom half, it's like I've taken that and inverted it, and the other chlorine sitting below forms the vertex of a second triangular pyramid pointing downward. Thus the name trigonal bipyramidal. This happens when you get 5 pairs of electrons around the central atom. My fifth basic shape comes from this. We'll illustrate with this compound, sulfur hexafluoride. Let's get the Lewis dot structure first. I get a total of 48 valence electrons. I join them with the sulfur in the center, and the 6 fluorines are arrayed around it. I've used up 12 electrons forming those 6 bonds. I've got 36 valence electrons left over. I go to the fluorines. They all each need 6 valence electrons apiece, which means I will have used up all 36 valence electrons. There are none left over, and sulfur in the center has a total of 12 valence electrons, which again is an expanded octet, but again that's okay because sulfur resides in the 3rd period or below where there is space for this. So I've got 6 pairs of electrons around the sulfur in the center. The furthest I can get them apart in space would be this sort of arrangement, where I have 4 fluorines going through the center of the molecule, and I've got 1 above and 1 below. So again, we have axial and we have equatorial positions. Axial to axial is 180 degrees. Those in the equator, they're pointing towards the vertices of a square. So I know that the diagonals of a square are perpendicular to each other, so I know that's 90 degrees. And then, of course, axial to equator is also 90 degrees. This is known as an octahedron, an 8-faced figure. So again, each three non-collinear points forms a plane, and I got 4 faces on top and 4 faces on bottom. It looks like jacks that you might have played when you were a little kid back in grade school, and you form an octahedron. Okay, so I've gone through 5 examples, and all 5 examples illustrate the 5 basic shapes. All other geometrical shapes of molecules are going to be based off of these 5 molecules, 5 shapes that we've come up with. Again, I greatly encourage you, read the book, go into chapter 6, and make sure you look at those diagrams. It'll make it much more understandable when you can see as many diagrams as possible. That's your job. You can't say, hey, I don't see it from your diagram. Then go look at other diagrams until you get it, because that's your part of this bargain. That's part of your job. Figure it out. You can do this. So let's look at examples then when you modify these basic shapes. So let's go to a 6th example. And we've seen this molecule before, ammonia, of course. And we're going to try to predict its shape. So we have to draw its Lewis dot structure. We have 8 valence electrons. We join the atoms with single bonds. I used up 6 in forming the bonds. I had 2 valence electrons left over. The hydrogens had their duets, and nitrogen now needed its octet. It's not an exception. And so we put the last 2 valence electrons on the nitrogen. Now, here's what we do when we've got VSEPR and we've got lone pairs. You still simply go to the central atom and you count up the number of pairs of electrons. It doesn't matter whether they're bonding pairs or they're lone pairs. They still are going to repel each other. They're going to try to get as far away from each other as possible. This is 4 pairs. If you think back to what you just viewed in the video, back with methane, you know that 4 pairs of electrons will point towards the vertices of what is known as a tetrahedron. But we don't have 4 atoms connected to the nitrogen. The 4th position is a pair of electrons, that lone pair. So it looks like the nitrogen is sitting at the top of a pyramid. And that's exactly what the shape of the molecule is. This is known as a trigonal pyramidal shape, or trigonal pyramid. The nitrogen sits at the top. The angles between the pairs of electrons would have been 109.5, but that lone pair on the nitrogen, they are held close to the nitrogen. They don't go very far away from it, and that particular electron cloud creates greater repulsion on what is essentially the 3 legs of a tripod. It pushes the legs closer together. The angle gets compressed down to 107.3 degrees. This is called trigonal pyramidal. It's a modification of the tetrahedron. So again, you have to know the basic shapes, and then you just describe any modifications like I just did with the introduction of that lone pair on the nitrogen in ammonia. Let's try another example. Here is water. Let's get its dot structure. And of course we had 8 valence electrons. We've seen this before. You've learned that this should be an angle. Well, now we're going to find out why. We go to the oxygen in the center. Again, we want to get the geometry. We count up the number of pairs of electrons. There are 4 pairs, 2 bonding pairs and 2 lone pairs. 4 pairs, again, want to get as far away from each other as possible. That would be towards the vertices of a tetrahedron. But 2 of those vertices are going to be empty because they're lone pairs, not another atom connected to the oxygen. And so what's left over is a molecule where the hydrogens are at an angle to each other. The 2 lone pairs are pointing towards the vertices of a tetrahedron, but the shape is based upon the actual atoms. And of course, we call this either bent, or some books call it angular, and still others might call this V-shaped. Now we've got 2 lone pairs. They compress that tetrahedral angle of 109.5 all the way down to 104.5, the angle I asked you to memorize. So again, we got the shape by looking at the modification of a fundamental shape that we'd already talked about in our 5 basic examples. Let's try another one. Sulfur tetrafluoride. You count up everything, you're going to get this dot structure. I'm kind of speeding things up here a little bit. Here's my dot structure. And I notice I go to sulfur, it's in the center. I want to get the shape, so I count the number of pairs around the sulfur. I don't care whether they're bonding pairs or lone pairs. If I add them up, I've got 5 of them. And in our fundamental shapes, 5 pairs would be pointing towards the vertices of a trigonal pyramid. And that's if we had 5 different atoms, 5 bonding pairs connected to the sulfur. But one of my pairs is going to be an empty space. So I have to choose whether that empty space will be in an axial position or in an equatorial position. And I want to arrange it where I'll give that lone pair more space, greater room, so that again we're trying to reduce the repulsion. And in this case, because of that, I'm going to put it in the equator. All right, and so I get this kind of arrangement where I've got sulfur and 2 of the fluorines, forming sort of like a backbone, which is part of the axial position. And now in the equator, there are only 2 other fluorines. And this shape really is very simple. We call this a seesaw or a teeter-totter or even a sawhorse. So again, it was a modification of a basic structure we already talked about. Again, if you don't quite understand how we got to this, look at the diagrams in your textbook. Figure it out. You can do this. Let's go to another example. Xenon tetrafluoride. Let's get its dot structure. All right. Got a total of 36 valence electrons. We take care with single bonds. Then we go around and take care of the fluorines. I've got 2 pair left over. I'll put those onto the xenon because it can have an expanded octet. So it looks like that. I want to get the geometry. So I go to the xenon. I count up the number of pairs of electrons. There are 4 bonding pairs and 2 lone pairs for a total of 6. In the fundamental shapes, this would be, those atoms would be pointing, those bonds would be pointing towards the vertices of an octahedron. But 2 of my positions, 2 of those pairs, are lone pairs. So I'm going to take away 2 of the positions. I'm going to give those lone pairs as much room as I can. I'll put them opposite each other. So it looks like this. And of course, what I've got left over, I've got those 5 atoms all in the same plane. So it's going to be a flattened figure. And they're going to point towards the vertices of a square. This is called square planar, which gave me a 90-degree angle between those bonds, those pairs of electrons. Again, check your textbook for some really wonderful diagrams. Let's go to a 10th one, sulfur dioxide. Let's get the dot structure. Add up the valence electrons. This one, once you figure it out, you see that we end up having a single bond and a double bond around the sulfur. And I still have 2 valence electrons left over after I do all that. And the last 2 I need on the sulfur, right, because it doesn't have its octet yet. So there's actually my final structure. But of course, having talked about dot structures, we know that double bond could have been on the other oxygen. So of course I get resonance structures, 2 of them. All right, now I'm trying to get the geometry though. All right, so I go to the sulfur and I count the number of pairs around the sulfur. However, be careful here. That double bond, those electrons are all in the same cloud. So that cloud only counts once. I don't count it as 2 different clouds. It's 1 cloud. So I've got 3 pairs, essentially, as far as repulsion goes, 3 areas of electron clouds. So they're going to try to get as far away from each other as they can. And those 3 electron clouds are going to point towards the vertices of a trigonal planar structure, but one of the positions will be empty, and so it's going to look like this. And so I don't have trigonal planar. This is simply, again, a bent or V-shaped or angular molecule. That angle can't be 120 degrees because of that lone pair. It would be less than 120. You don't need to memorize that particular angle. All right, so when you've got a double bond, that counts as 1 cloud, though. As far as pairing, as far as repulsion of electrons goes. So you got to differentiate between a double bond, 2 pairs, and just simply 1 area where you got 4 electrons orbiting back and forth. Okay, you have to, again, figure it out. This is not hard to remember. Straighten it out. All right, let's go through one final example. Well, there's your 120 degrees. Let's go through one last example here. Bromine pentafluoride. Let's get its dot structures, and then we'll see what we come up with. Here's your 5 fluorines. Took care of 10 electrons. Take care of the fluorines. You still have 2 left over. Put the last 2 on the bromine. It's allowed to have an expanded octet. You have 6 pairs of electrons around the bromine. 6 pairs again. The fundamental structure would have been an octahedron. And of course, in this case, it's going to be modified in 1 position. It's totally symmetrical structure. It doesn't matter where that lone pair is located. You're going to end up with this kind of structure. Okay, there's your 5 fluorines and there's your lone pair. And of course, again, you describe what you've got now, and it looks like you got that fluorine sitting on top at the apex of a pyramid, and you name pyramids by describing the shape of the base, which is square. So it's a square pyramid. That is how you determine the geometrical shapes. You start with the dot structures, and then you go to arrangements trying to reduce the tension, the repulsion between the electrons, electron pairs, electron clouds, however you want to phrase it, and that's called the VSEPR model. Again, read your book, look at as many pictures as you can, become comfortable with this. You've got to work at this. Some of you are going to have a tougher time trying to imagine what these diagrams look like. That isn't a reason to not try. You still have to try, and again, I'm confident that you will get this, but you're going to have to work on it. It doesn't come easy.